a veteran trainer for the AI for the real life applications who will be taking this session on deep learning in medicine, images, text, and signals. Today, we have an interesting surprise that there will be a hands-on for testing how we can actually use those particular machine learning applications in the medicine in real life. To moderate this session, we have Mr. Ravi Bhardwaj, who is a senior leader in GE Healthcare. That's what we see as a bridge between research and application in real life. Over to you, Neil. Eager to hear what you're going to teach us today. And then happy to participate.
Thank you very much, Suresh sir and Ravi. I'll just share my screen. Hope it's visible in the full screen.
Yes, sir.
Okay,
Yes.
great. Hi, everyone. Good evening. So let's dive into the module 9. In the agenda today, we will be doing a small recap of machine learning and continue with the intuition that lecture 8 started. And then we will see how deep learning works at a superficial level. And we will also get to discuss the main use cases, medical imaging and medical signal processing like ECG and EEG, and then medical text processing using generative AI, LLM, and GPTs, which is being very famous in last few years. In between, we'll try to see the demo also, which gives us a intuition how things work, and the links will be part of the slide. If it is shared, everybody can play with it. So this important disclaimer, this total slide is only for information, and some of the things are actually may not be factually medically accurate. So these are only for representational and illustration purpose. There is absolutely no medical advice that should be extracted from this session. Those are all for illustration. All the views presented are personal, not related to any employer or any institution. And then all we know that the deep learning and machine learning in general is a very fast moving field. So anything that we discuss today may get replaced by a newer version or a newer technique. So it should not be treated as all time, treated as so that it doesn't hold, because it may not hold true in all time. So the very meta question, the first question everybody in the clinician community might ask, why should we care about all this? Because we are a consumer of the technology. Why should we care how the technology is built and how it works? My answer to that is to set the right expectation. So imagine you are traveling from your house to work and Google Maps shows 30 minutes. So it's not a guarantee that Google Map gives 30 minutes. It's just an estimation. It's an estimation based on everybody else's data that has been captured. It's based on time of the day, if it is office hours or not. And it's also estimation between if it's a weekend or weekday, all those factors. So there is no guarantee. So you should always plan for it and take some buffer, and don't commit anybody that you are going to reach and show up in their door in 30 minutes. Similarly, when we work on medical AI, most of the things and everything is prediction. It should not be taken as a gospel truth, and human moderation is mandatory in that. That's where the human factor, human in the loop, comes in. So as most of the lectures so far has been discussed, that how these three things are related. The traditional AI, those were hard-coded rules that is encoded in the device, and when the parameter crosses those thresholds, it gives us a signal. For example, a smart thermometer, the only smartness it has is it just checks the number and gives a color code based on that. But in machine learning, nothing is pre-coded or encoded earlier. It is trained over real data, and those real features are extracted by the clinicians by looking at, for example, the size of the tumor from an X-ray image, or PET scan or any other blood test report markers. All those values are inputted to train a model, and then using that model, things are predicted if it's a high risk or what category of disease it is. But it gets more complex into following two factors. When the data set and the size of the parameters, too many biomarkers, and there are a lot of input variables, the size of the variable increases a lot, then machine learning struggles. And also, not everything is a structured data. Like not everybody can manually extract all the data from binary uh, artifacts like images and text and signals. So deep learning will let the machine learn on its own automatically and extract the feature. In deep learning, it decides automatically what is important for prediction and what is not, so that we don't lose the entire X-ray images, texture, and all the pixels, and we don't lose the information which is not extracted by the clinician. Take a very simple example to illustrate how these things are different. In a hypothetical scenario, for example, let's say we are trying to predict the risk factor for a patient based on a single variable, blood glucose. We all know that after a certain threshold of the glucose, the risk factor increases, and it's a simple number beyond which we declare the patient is high risk. But in reality, that is not true. Think of the scenario two, where both the BMI, the weight of the patient, and glucose is taken into consideration. At that time, the line doesn't remain straight anymore. If you see the patient who are here, they're clearly in the red zone, although the glucose value is much lower than usual. That is because the other parameter, uh, which is the BMI and weight, that is too high. So although the patient has a lower glucose value, they had to be in the red zone. So here the decision boundary becomes a bit slanting, not really horizontal, which is depending on single variable. So consider this sample calculation, how one can create a risk factor. If certain weight 0.5 is multiplied with BMI and another weight 0.8 is multiplied with the blood glucose value. If you see the weight of the glucose value is higher, that means it's impacting more to the score. However, the BMI is impacting less. So these are two different weighted variables which are added together and score is obtained. The 100 fixed number is nothing but an adjustment factor, because we want the score, when we decide something, we want the score to be centered around 0. So uh, what do we do with the score? How do we calculate chance or probability of the risk from the score? We pass it through something called activation function. So in activation function, there is an input, which is a number, and the output is always between 0 to 1. That means the probability cannot go below 0 or higher than 1. The risk is highest at 1, the risk is lowest at 0. And we see that this line is also not flat. It is starting flat and then it shoots up around 0, and then it again flattens towards the 1. So there is an inflection point at 0 where it is most indecisive. If the score is much lower, we know that it is not diabetic, so we don't care much, we don't think about it much. If the score is way much higher, then we know that it's a diabetic and the risk is very high. But machine learning helps us decide between the borderline scores, where a little change in the score based on the input variable and multiplied by weight can change the risk factor uh, in the other side of the park. That means we declare that it's a high risk. That's why the activation function is called a sigmoid function. It's also called a regression, a logistic function. That's why you must have heard the term logistic regression a lot in the. So ultimately, in this risk calculation, output can be represented by a small network like this, where there are two inputs, it's getting multiplied and then passed through a function. So output is a single number, which tells us the score. So since you all are clinician, not really It's not a unknown factor that artificial neuron, which is used in machine learning concept called perceptron, is actually inspired from biological neuron, where there is hundreds and millions of dendrites which is receiving signals from other neurons, and those signals can be either fire or don't fire. I think it's called inhibitory uh, and fire. So there are some input which is saying fire, the some input saying don't fire. At the center, the cell is like a calculator. It adds up all the fire and non-fire signals, and if the net signal is fire, then it says the next activation potential to give a signal. Otherwise, it doesn't do anything. So it's all or nothing. And then again, the same story, other neurons are connected to it. Similarly, in artificial neural network, this is the very simplest case. There are much more perceptrons that can be chained together and connected together to get the output. Because the in case of even in case of diabetics risk factor, we may have other variables, and it may not be straightforward just multiplying two factors and passing it through a function. There are things are more complex when it comes to images and detections and text. So there are much more many layers in between what we see. We see the input, we see the output, but we don't see the in between layers. That's why they are called hidden layers. And there could be thousands of and hundreds and millions of hidden layer for a complex model. But now we know the input and we want to get the output. What is unknown? uh, for a training data set, we have the input and we have the output. Those are the labeled data. We have X-ray image and we know the output if it is a tumor or not. But how do we learn? How do we train this? So we train with something called feed forward. So that's like learn by doing. When we say a child that you learn by doing for any kind of skill, they do some random things first, and they might fail, they might pass. If they pass, they know what to do. If they fail, they don't. They course correct. They know what not to do and try different things. Similarly, for training images, we give input and we know the output already, and we initialize the intermediate multiplication factor that we called weights with some random numbers because we don't know them. And when we get the output, we get, obviously there are chances that we output is wrong because this is not a trained model at all. And then we compare the known output with the output that we incidentally got, and this, there is a difference, and larger the difference, we know the adjustment needs to be the adjustment needs to be done more. So we try to adjust the initially assumed weights like 42 or whatever number we assumed. If it is close, we do smaller adjustment so that it converges to the desired output. And the way we do it is called back propagation. That means we feedback the signals that we got, that there is an error, it's a large error, it's a small error, we feedback, and through the back propagation, the weights are adjusted. And this cycle goes over and over million times. Finally, when the output is converged and our learning algorithm is happy that, hey, now any input that we give, it will predict the output because we have learned enough. That means we have decided the values of the hidden layer enough, and it should be able to give the output for the unknown images. So coming to application, there are three main application, like from the title of the lecture, because these are the data which cannot be quantified easily. For example, medical imaging. These are all photo data. Photo data cannot be quantified with single number or multiple numbers. So there's a technique called convolutional neural network that is used to segment the images uh, or classify the disease or any other analysis. And for medical signals like EEG and ECG, those are not static images or static snapshot. Those are, I agree, it's a lower dimension value. That means it's a single voltage value, that is, but it is temporal. It is changing along with time. So it comes with a new image, new challenges. So for that, there is a version of neural network algorithm called recurrent neural network is used, and also LSTM for some complex cases. We'll learn about it later. And medical text, it is there is a huge number of corpus, be it medical health record, be it literature, and even these days there are a lot of feedback crunching that is happening either from social media or the survey links. All those things are a case of deep learning, because those cannot be quantified using numbers very easily. Let's get to the imaging first. How do we acquire the image in the first place? We all know it's a sensor that is in one of these X-ray machines or MRI machines that captures analog signals either by deflection of X-rays or magnetic resonance. So those analog signals are converted to digital signals to the pixel representation. In the previous lecture, you might remember MS Dhoni's photo that was represented at pixel, and there was a numeric 8 that was represented as a pixel. And it's a grid of numbers. The darker the pixel, lower the number, the brighter the pixel, higher the number. And if it's a color image, every pixel has three values, RBG. So because with three different values, we can know the intensity of three different primary colors, and the composite of those three primary colors gives us the actual colors. So it's just a lot of data and a lot of packed numbers in the matrix. If you have ever done photo editing in Photoshop, you must have seen these kind of histogram, what I in the left side. This basically says the density of the pixel. That means if there are large black pixels, then the black histogram is smaller, the black side of the histogram is smaller. If there are more brighter pixel, it is larger, which is this case, the histogram is larger. So if it is underexposed, then we know that there is not a lot of data there, so a lot of black pixel will come. If it is overexposed, that means the data is overwritten, and there is hardly anything to make sense of, then we can detect from the machine can detect if it is a quality image or not. Then it is sent to the processing. Now the neural network that we saw decides what kind of image is this, where is the organ, where is the tumor, all the detection, classification, and segmentation. Let's bit deep dive how exactly what happens inside the network. We have shown input layer, hidden layer, and output layer. Input layer is nothing but raw data that we obtained from the sensor and digitized as form of a two-dimensional matrix, bunch of numbers essentially. In the first early layers, they don't know much about the classification, complex disease or anything. They are just employed to detect fundamental image properties like a horizontal edge or vertical edge if there is a uh, in the image. So those are very general purpose layers. But at a mid level, it starts to detect more complex features like texture and shape. But these are all based on the previous layer uh, that already detected horizontal and vertical edges. These are not looking into the massive amount of pixel that was input in the step one. So the step three is basically getting only the output of step two, which is basically something called feature map. That means where are the horizontal image, where are the vertical image, vertical lines. At the end of towards the right side, at the later stage of the layers, the network starts to recognize complex uh, features, and these are medically relevant usually, so it's a domain relevant. It can detect the disease patterns, it can detect if whatever is going to be recognized as an organ boundary, and so such things. And eventually, because this is massive scale of data, they are there is something called pooling layers where it is downsampled. That means only representative pixels are sent forward. That means if there is a patch and all are same, then only the representative pixel is sent out, so that the size of the final feature map is small, something we can make sense out of it as a human, and uh, gives the output, and finally the decision is made. So if you see, the first few layers are very generic. It can actually work for flowers and cats and dogs, but the later few are very domain specific, which is medically relevant and disease specific. The first use case of all these are segmentation. So because uh, like human or any other fixed computer algorithm, it doesn't look at the pixel it doesn't look at the pixel and tells if it is part of the organ or not. It All the pixels are mapped to a probability if it is part of the organ or tumor or not, because it is neighbor aware. So even if the image in images it looks the same, because it has the context, the model neural network has the context, it's able to distinguish it is part of the organ or tumor or not. And it is also great at drawing the map of the organ, because you need to know where kidney is, where is the boundary of the lungs and everything. In typical images, the boundary is not very uniform, the boundary is not closed. There are some tissue which overlaps with each other, but because it has seen enough images of full other various sides of the organ, it is able to close the loop and help us detect where it is. There are cases where the patient comes with images over the period of time, June, January, every 6 months. So we want to track the volume and growth of any disease. So what happens is every time this scan, there is a probability the patient is aligned in a different way. For example, when you scan using your mobile phone a document, you see it is a bit distorted, right? It's not exactly perfect rectangle. So, but because machine learning, the neural network has seen how to treat all these images, it can wrap around and do a spatial transformation to make all the images look like exactly same and overlap on top of each other, so that a clinician can take a decision if it is growing or shrinking, and uh, what is the rate of it. And obviously you all might know, those who are radiologists, that uh, when the machines take 3D pictures, those are nothing but a lot of 2D slices. So it's not continuous. It's like stacking a lot of parathas and saying that it's a 2D. So there are edges in between, there are gaps in between which are not really mapped. So what traditionally it does is takes an average. So it is first of all misrepresented the gaps, and second of all, those are not smooth. So it's really helps, neural network really helps to predict the edges which are missing and make a continuous 3D volume for better surgical planning. And given an image, it can also augment when two pixel looks the same. It can actually internally tag the regions which look the same in different labels. We cannot see that, but in electronic form, it can tag in different labels that the same pixel is a bone or a tumor, although it looks the same, so that further processing, when it goes, those patches are distinguishable. So it does a digital signature and labeling behind the scenes. Next is classification. So traditionally, when somebody looks at imaging, they look at the local, let's say, uh, local anomaly detection. I want to see a 5 centimeter or 2 centimeter circle, which is different patch. Those kind of matching and decision making happens. But because neural network has a spatial context, it even if the pattern that we are trying to match as a circle doesn't match exactly circle, it's rough edges, incomplete edges, it is able to find the anomalies into that, so it's more accurate. Even for stage classification, uh, typically if there is a protocol, again this is very hypothetical data from a non-medical practitioner, that if a 2 centimeter tumor is stage 1 or certain stage, more than that, then we calculate the stage based on just that number, the radius of the tumor. But in case of neural network, it not just the radius, a lot of other feature which is not very evident can be taken into consideration, and mapping into a space where in the past it knows from other images and other models that where are the stage 3 patient or where are the certain stage patient belong to, what kind of feature they exhibit. So it can actually create calculate a distance and try to put them on that section, put the unknown patients. Even for predictive diagnostic, this is to predict for future because it has seen a lot of progression. For example, I was reading one of the articles. The location of a placenta can decide if the complication will be developing in the later stage of the pregnancy. Just an example. So because it has seen the journey of pregnancy for other patients, it can actually predict based on the location what is the probability of developing complexion. These are very hard to do manually, and even for the most experienced person, it's very difficult to do. High volume of image pre-screening, we know if the input, the population is huge and the medical facilities are less, this is one of the way neural network can prioritize based on the scan. As soon as the scan is out, the image is out, it can be run through the neural network and deep learning, and they can be put in the front because it's a critical case and should be consulted earlier. Not just image, because it can handle other form of input. For example, while looking at the x-ray of a chest x-ray, there is a respiratory data that is fed. So all these raw signal can combine, and they can give you a higher accurate prediction and result instead of just blinded by one single dimension. And the last use case is image reconstruction. In this case, the synthetic in this case, a not so great image which is not up to the standard can be fixed. Example, uh, there is a lower there is a patient who cannot take higher radiation for some reason, for anatomical reason. Then the lower radiation, which is CT images, which is not a lot, not clear a lot, that can be extrapolated and reconstructed to give an image. Even somebody without a contrast, because it has seen with and without contrast of other images during training phase, it can extrapolate and guess what would be the image if the contrast were given during the CT scan. And during a time of emergency or a lot of volume, faster scanning, which gives partial data, can be synthesized to give the higher data. Something called UNet CNN is used for that, where less amount of or a bad quality images can be enhanced to give a good quality image. And it is also used a lot of photo application. You must have seen in some of the application, they do a enhance my old 1940s 1950s image and they can reconstruct it. And these are the techniques. So a lower resolution image can be extrapolated to higher resolution image. Then due to some patient movement during the scan or some object or some implant they have in the body, those things can be removed artificially using neural network, because in the training phase it has seen such variation of image, and it has seen actually how the organ looks like. So this is one of the very common use cases. Then every machine is different, every settings in every hospital is different. So if there are noise emitting from there, it helps denoising those images. If you have done photography, there is a lot of sometimes a photo is taken with the camera cap on it, so that totally black images, that means only the noise from the camera will be captured, so that when the real image is captured, the noise is subtracted so that we get only the signal data. And this is a very modern use case where we synthesize the image altogether, like generating a lot of when there is a scarcity of input images and sample images for training, it can generate a diverse set of images with a lot of variation and feed it to the neural network to train the model. And we all know that certain race, certain age, and certain countries people's data is available, but when the model is but the model needs a very good balance and very diverse people. When the model is applied on another set of population, it doesn't do well. So it can construct a model which is not biased and fulfill the gap of training data. And this also helps us creating synthetic images which can be shared with research organization by preserving the actual data of the patient. That's like a gold mine for any research organization. rare disease, there is always lack of data. Synthesis of image can really train the model. Then we all know that all the machines, we have images for some machines, some diagnostic machines, but not all vendors. And this uses neural network can be used to generate artificially what if this image was taken in a different machine. In fact, there are use cases where you have a CT scan but not enough uh, other type of scan, let's say X-ray. It can be transferred and translated cross modality because it has seen both kind of images, and certain model can actually fulfill the gap. And the recent development of medical image embedding is the highest, probably the buzzword right now. Uh, what is embedding? Imagine you are in a supermarket, you are trying to buy something, and you know that similar things are kept together. So fruits are kept in a place, eatables are kept in a place. But if you're trying to buy a toilet soap, it's probably farther away. You have to walk a lot. And within fruit, the similar fruits are again are kept together. Apples are together. You will not find apples in two different sections. So we know that similar things have a similar, very less distance with each other. And in medical terms, when images are represented as numbers, a vector. So if you see in the bottom, X-ray images is represent a series of numbers. And if those are plotted in a space, obviously beyond 3 dimension we cannot see. But imagine it's a 3 dimension space. There are three numbers representing a picture. You will always see similar pictures will be together. So if we can calculate the distance between two images, we know that these two are X-ray images. And if those are very far apart, then we know these are different images. If a normal X-ray and an abnormal X-ray are kept together, normal X-rays will be together and the abnormal X-ray will be a bit far than the normal X-ray. So the distance, from the distance, we can know that how similar two things are. And because of LLM and generative AI, deriving these numbers from models become very easy. Hence, taking a decision and deciding if things are same or different has become very easy. The use cases, you all might know that PACS is the repository where all the medical data is stored. So sometimes when you're searching something, a very specific image, let's say I want to find an X-ray of a past patient with a similar ground glass opacity for the chest X-ray, then so the images, when it was deposited, it might not have been labeled properly. Nobody wrote on top of it, or it's not entered in the system. In that case, it becomes very difficult to search. But because we know the uh, any image which has a certain feature together, we can actually calculate the distance and fetch it out. I mean, this looks like a magic, but it's actually just simple math. Then again, we saw in the X-ray, we saw in the neural network that earlier layers uh, give a very generic, general purpose features like vertical and horizontal line. So here, if we have a limited sample and we have the embedding models, for example, we can have very limited sample of a rare disease. There's something called transfer learning, where a general purpose model can be augmented with some specific images to create a model which caters to that specific disease. So it helps with less data. Then zero sort classification is where we haven't seen, this is just an example. Obviously, these are very popular cases. Let's say there's an image which we don't have in the repository, and somebody is trying to search malignant tumor. Although one is text, you are searching an image with a text whose image is not available. Because these two mean very similar in semantically in English, the images and the text, these two mean the same thing, they will be plotted in together in the space, in embedding space. So it becomes very easy to search by name, because the model has seen the word malignant tumor. Somebody in the text in the input text has written that what are the properties of malignant tumor. And when we also analyze the image, we also have seen what are the property that image has, and then property and property matches, because the properties actually decide where we are in the space, what is the distance. So although one is text, one is image, the distance is very less. Now let's see, we can see the demo. This will open in a new tab. Let me know if it is not visible.
Yeah, it's good.
Yeah. So the first demo is outlier detector. Where is the anomaly? So if I go there and let's try, these are publicly available link. You can try it as well later. There is a lot of slides loaded here, 24 slides, but we're looking at this slide, first slide. So if you zoom into this, it has some guidance just for our convenience. I can remove the guidance here. Let's say I want to know where are the anomalies. So this image is already, yeah, I just hit detect button. So what it does, it goes through every pixel, and if some pixels are very different from the neighborhood pixel, it flags it as anomaly. So if you see the red is basically, it decides that it is not very same as its neighborhood. So it flagged these two places, possibly a tumor or a problematic patch. And if you see in the guidance, the uh, red is when it is not matching the neighborhood, and blue is the other part where it is a smooth transition, it's matching the neighborhood. So it is because of the embeddings, it could find the distance with the neighborhood. Wherever the distance with the neighborhood is different, not the physical distance here, the distance of feature, then it flags it. So let's go and do another experiment on the same slide again. This is classification. Here we will be training it instead of whatever it decides. It's the same slide again. We remember there was anomaly here and anomaly here. Now let's say the pathologist comes and see that, okay, I found one anomaly. Where are the other anomalies here? So let me first train the classifier. Whatever I know this is anomaly. So I'm going to circle it, and I will ask it to train that, hey model, get trained on this kind of anomaly. And it says it is training, started, completed. Now I want every patch, every place, where are all the same, whatever I showed it, can you find it? So I'll do a detect. It will not find anything else. It will only find the one it is trained on. So it found a similar patch here again, which is again red because uh, it is very similar to the patch that I trained on. Blue is a low confidence. It could be, but very less chance. I can slide this left and right, and let's say I need only the very high confidence one. I don't have time, or it's an emergency situation. I might slide it to right so that only the high confidence patches are shown. So these are all happening real time when the embedding is calculated in the server. So it doesn't have to go through a neural network and create a model. It's purely based on the calculations and the distance measurement of the feature that it can see pixel by pixel. Let's go back to the slide. Okay, hopefully we're back to the slide. And okay,
Yep.
now let's tackle another type of modality, that is signals. We all know signal is simple, it's a voltage, one dimensional, but it has another dimension called time, which is sliding one after another. So it doesn't make sense to look at, we all know that it doesn't make sense to look at only just one snapshot. We need to see the trend, where it is going, what happened just 1 minute before, what happened just 5 minutes before. So there is a moving window that is going on. And like earlier I mentioned, the recurrent neural network, it considers the previous window as well, what happened in the patterns that was seen in the previous window. And there is something called long short term memory, LSTM, that actually retains memory of a bit further in the past, so that it doesn't forget what it has seen, because the trend is usually larger than just one small window. So in long short term, because it has a long memory, a fraction of it, not all the long term memory, but it also operates on the short term memory. It combines both of them and try to make sense out of it. If something is going to happen, if some trend is observed, it's like you are reading a book and you are just reading the words individually. You are not remembering what was the beginning of the sentence. Then it cannot make sense out of it. So you all know that in a typical ECG, you have a P wave, which is the upper chambers pumping the blood to lower chamber, and then QRS, which is the lower chamber pumping to the rest of the body and lungs. And finally, the T wave, when the lower chamber contracts and comes back to the restored to the original position. So individual, these patterns can be found out in the initial layer of the neural network. You remember we detected edges in the beginning in case of photo. Here, individual patterns will be detected in the initial layers. In the middle and the final layers, it will find patterns of patterns. What happens when, what are the pattern when P, Q, R, S complex and T all are seen together? So that can detect at a later stage of the window if there is a problematic, if the patient is going through something right now or it is trending towards something. So, and the another way of removing the noise is max pooling. That means it ignores all the small little blips which is at the baseline, which are noise from the devices and everything, and rectifier ReLU they call it, so that only the top signals, relevant signals, are taken into consideration while running through the models. So with all signals combined, it solves the problem of blind spot. Let's say I'm creating a self-driving car, artificial intelligence. I will not only look at the camera, what is in front. I will also look at the sound, somebody is honking or not, or I'll use a radar signal if the camera is blinded by the sunlight. So there is multiple signal going through together, and neural network models can synchronize them with time and then find sense out of it. So it is very difficult for a human to look a lot of signals together, and it is possible with the experienced physician, but machines do not get tired and they have a lot of compute. So taking the AI's help always increases the efficiency. And obviously, because if you see the signal in silo, like heart rate is rising, it might not tell us much if the other signals are not present at the same time, like the respiratory system signals. And finally, this is a use case which is uh, s- very near to my own work as well, because as a programmer engineer, you do a lot of coding, and code is text. The code generation has become very easy in last few years due to generative AI. But in case of medical text as well, imagine a patient and a conversation between patient and doctor, and the doctor do not have to write anything, or the assistant or anybody else do not have to be present in the room, and the audio can be recorded. And audio speech to text synthesis conversion has been very accurate recently due to generative AI. And even the text is in a unstructured manner as a paragraph, extracting vitals out of it, medication out of it, timings of the medication out of it. Those has become very easy from raw text to structured data. There's a spreadsheet linked at the end of the slide. You can go and check, play with it. Some fake data is there in Google Sheet. One can use it. Totally artificial data. One can play with it, how it works, just for educational purpose. Then with the clinical history, if the doctor's clinician starts flipping 50 pages over and over, 15 years of history, it takes a lot of time. Rather than A neural network, deep learning can help highlight the actual medicine condition or any reaction that happened in the past. Those are the important things you get asked, right, by the physicians whenever you present yourself. Those can be highlighted. And then for clinical research also, because there is a lot of historical data with charts and efficacy and everything, so it helps us drill deep into it and find those top 5 patients who are actually more probable for the trial. it, it does really a great search in that case. Some of the real examples of transformer algorithm. Transformer, the word you might have heard in the context of ChatGPT and Copilot, all those tools, is nothing but the whole sentence is semantically looked at. Uh, what is the meaning of it, not just individual bag of words. So if the patient feels cold, it could be temperature, or patient caught cold. So the same word cold means two different things here. But thanks to the transformer architecture, the tools like ChatGPT and Copilot are able to make sense out of it, and it's able to converse with you with meaningful meaning of it. Earlier, how the rudimentary web search used to work is, if the cold is present in a document, it will just present to you. It might be some other cold, you probably meant something else, because it used to be just basic word matching, or the frequency of word that is present in a document, how rare the word is. Those kind of parameter it used to work with. Then they're able to train models on a general purpose model, which is based out of the total internet, with a lot of comment, which may not be from verified user, may not be somebody's frustration. So there is a lot of content in the internet which is not reliable in search, right? But these days they're able to train medical specific model from specific sources, like PubMed is more reputed than any random text that is found in the internet. So you might have seen these parameters, temperature and thinking level, while using ChatGPT and Copilot, all those tools. It basically means how much of creativity you want. Uh, the higher the temperature means it can generate some random things out of creativity. But if you make the temperature 0, that means it will be very strict, and only the confident values will be given to you. And finally, even if it's not directly related to medical, but patient care, admin use cases are a lot, which patient spends a lot of time before even getting to a consultant or a diagnostic counter, is patient registration. I've seen a lot of hospital has kiosk in front of them, but that's, again, not everybody is familiar with it. What if somebody could just write the form, which they are very fast at, and the form is scanned and automatically all the data is taken into the computer, instead of an operator having to type and having to wait for 10 minutes. These things are really useful in administrative use case. Let's say there are meetings, those can be transcribed. Even at our work, meetings are transcribed, and nobody listens to the video all over again, the recording. They only, even this YouTube video, you can just click a button and see what was the summary of it. You don't have to listen for 1 hour later on. And there are a lot of policy documents, there's a lot of big documents, but you need a specific answer. Let's say you have one question, you don't have to read the entire repository of document. You can actually chat with those sources of information and get your data right back. It's very similar to how ChatGPT, you can upload a file and ask the question out of it. So if your organization, your hospital is implementing all these things, it becomes a very time saver for everyone, both patient or the administrative staff. Sorry. There are a few more demos. I would encourage you, once you get hold of the slide, to click and play along with, like I played with one of them. There's a spreadsheet at the end. You can actually, it's very experimental. You can translate from one language to another. You can extract data from a large medical history with it's and really reduce cognitive load of a healthcare professional using the latest tools. These are my coordinates. Feel free to send a DM. I know there's a lot of things covered in this short time in this slide. I just wanted to touch everything on the top so that we know the landscape, and then we all have access to the web and tools, and we know how to search more in-depth knowledge about it. And there are upcoming lectures also covering in depth in every aspect of it. So feel free to get clarification. I'll probably sit down in a weekend and answer everything. And this is the LinkedIn QR code you can scan later on. Thank you very much. That would be it from my side. Over to you, Ravi sir and Suresh sir.
Thank you, Neil. This was, of course, very absorbing, and actually you covered a good sense of the landscape. I see that the chat is filled up with a lot of curious questions, and maybe I will pick a few, right, and then we can. Firstly, there was a question on whether the imaging that you showed is extrapolatable. Can you extrapolate it to histopath images? I did say yes, but you can touch a line on it before I go to the next one. Please go ahead.
Were you talking about generating synthetic images?
This was more about segmentation and examples that you gave for imaging. I think there are pathologists in the group. They would want to know how does this apply? Does it apply to histopath images? And then
Yeah. So the examples I chose was purely
yeah,
from a radiology and X-rays and CT scans. There are very less examples. It's a very uncommon area of data source in the internet, but definitely it applies to histopathology. You must have seen my demo there. Actually, the slides were
yes,
histopathology. I was really glad to see that they have this in the data set, and there were 24 data set. So the machine learning doesn't distinguish between what kind of image it is. For them, it is just pixel, right? So if they are good at finding patterns, so if there are enough pathological slides in a training data set, they should be able to predict as well.
got it. Next question was an interesting one. Is there a model for detecting hallucinations in the ML? Right. I think it was a
It's like a
yeah.
like a
Go ahead.
self-critical model, because how do you trust it in the first place? So yeah, first of all, whenever something is deployed in medical field is very well tested. I told about the temperature, right? The temperature is actually kept such a way that it is not going to give you an answer unless it is sure. It can still hallucinate, but the chances, we all know what is the stakes in the medical, as opposed to writing any bad code. Nothing will happen much unless it is deployed in a critical system like a medical facility. So first of all, those things are taken care. That's why the innovation is a bit slow. People generate coding models every other day, but you don't see people generating medical models every other day. Only the big shot organizations which has a lot of horsepower and research facilities to allow it. So about detecting, it's always uh, what I do for what I do for my work is I always cross question. Like there is something called explainability, right? If how did you arrive at it? If it cannot explain or it cannot show me the intermediate stage, I know a lot of intermediate stage doesn't make sense for human. It's sort of a black box, but engineers and researchers are trying hard to make understand the intermediate nodes and intermediate decisions, which leads to the final decision. So there it can help to some extent.
Yeah. That's good. Okay. Couple of other questions more related to how this can be applied to other fields. There was a question on can we use these in mental health? There's one more, or can we use this on EEG and EMG for muscle activation detection? So there were questions on how broad can we take this. So maybe you can touch with a couple of, including fractures in X-rays, etc. Right? So you could touch upon a little about an example in some of these.
Yeah,
In
I think
other,
yeah, sure. Yeah, I think it connects back to the first question again, because again, AI sees the pattern. If the model has enough fractured images, it can actually detect between fractured and non-fractured, and also it can segment where exactly is the fracture. If the model has most of the images are COVID-19 a chest X-ray, obviously the efficacy of detection of fracture will be very less. So there is one of the examples in my demo, one of the links. It actually detects a lot of X-rays if there is a fracture or not. But in simple, because I'm not a medical professional, I will not go deep into it. But as long as there is a image, it's a pattern, it's a pixels, everything can be detected, be it apple to orange distinction or there is a hairline fracture or not.
Got it. Nice. One other question was, there are a group of questions on artifacts. How do you remove artifacts? How do you make the images more clean, etc.? And what kind of software can be used? And maybe you can touch upon any open source models or are such
Yeah.
models.
Okay. I don't have anything open source top of my mind directly, but I'll have to I'll have to check because I haven't done hands-on on these. So anything I tell will not be
Yeah,
justifying the
yeah,
thing. But yeah, definitely denoising is a very common thing.
yeah.
There is something called diffusion model. So what it does is generates artificial images. But when it is, I told something called UNet, right? The model training looks like a U. So it takes a noisy image, it extracts the feature, and then it puts back the context of the overall image so that the extracted feature is superimposed on the original image as a noise-free artifact.
Got it. Thank you. One question from my side, right? Based on what I'm looking at in the chat, when a clinician is being asked to use an AI model or a product that contains AI in it, right? How should they approach it? And today they're doing their work based on how they've been trained by their seniors during residency and in their education, and then day-to-day patient experience that they gain. When you are given an AI model that sort of tries to solve those things that they practice in their daily life, what should they keep in mind? How should they approach taking it into practice?
Yeah. So generally, as a clinician, I would think that the models are deployed as part of some other tools. They will not probably interact with the model directly. It will be part of some other software wrapper, which is basically our job as an application engineer. So we wrap the software in and with the underlying model. I think it's really important to understand whatever we have learned so far in till lecture 8. Everybody has been saying that the final decision is with human, and whatever the output from the AI model is, it is just to assist you, not to replace you. So what happens is, the first thing I would do if I'm asked by an organization to give a tool, I am actually using a lot of AI tools. I would look at the documentation of it, and it's the tool or application creator's responsibility to declare if what kind of data set it works on. If it is biased, they should declare the efficacy on different segment of people. If it is meant for western races, or it is meant for small kids, or so I would expect those things in the documentation and internalize it so that I can trust it. And the second factor is, I was telling, is explainability. I will also look for a documentation where it tells me how it arrived at an outcome. Can it give me intermediate images? Can it pinpoint, you said it's a problematic patient, can you highlight the section and tell me so that I can double check? So these are the questions I would ask to the vendor even before purchasing a AI tool, and as a user I would consult the documentation.
Thank you, Ravi, and thank you, Neil, for such a great presentation. First of all, no, it is a lot of things. For those who are asking for demo links, you can just scroll back into the presentation and it is very much available there. You can just, it's at the end of the presentation, last but couple of slides, wherever Neil has presented, the demo links were there. Neil, I have only 30 seconds, quick answer. So there is a very interesting question from the dentistry department that I see. If I'm doing a prosthodontics, if I can't just speak out, and if at a partial anesthetized, by just looking at my face, can you draw the pain score by the facial expressions and other things? Because it is static dynamic also. It is not like ECG. It is not like MRI. Very interesting question that was that I saw there. Is it
The
practical?
change in expression we have to detect. Yeah, I'm pretty sure theoretical is definitely possible, but I won't know if somebody is really working on it, because I
If at all
personally would
someone
like.
want to work on it, technically feasible.
Yes, definitely, because it is a quite distinctive expression that somebody gives. With enough training data, I think it's possible.
I think this is a good example of natural intelligence. They probably will shake their hands or legs
Right.
and will make a sound saying, ah. I think at this point, natural
Yeah.
intelligence is probably sufficient. And if they want, they can use, but
Facial
frowning
expression sort of
and
thing.
blinks,
Frowning
like
and
a simple code saying blink twice if it's painful or whatever.
Right.
It's totally humans' responsibility to capture those signals. Without those signals, a machine cannot do anything.
Got it. So thank you very much, Neil and Ravi. We have a lot of questions. Thank you, Ravi, for actually summarizing them. I saw more than 1,000 questions, and it is embedded within the noise. That's what is actually that's making it is more difficult. Over to you, NBMS, for final comments or closure. Nothing is there? Then we end the session here. Thank you very much.
Thank you.
Thank you.
Thank you, Neil sir and Ravi sir and Dr. Suresh sir for this wonderful session. Thank you all of you. Thank you so much for joining the session.